Hello, we are on the second video for proportions and we're on this question about landscaping. So we're going to get started. So first you would always want, of course, to read this question because as you can see it's pretty wordy. A landscaper is designing a garden for a house that is not yet built. He needs to determine how long a shadow the house will cast in the garden area. To determine this, the landscaper, who is 6 feet tall, measures his shadow to be 8 feet long at a particular time on a summer afternoon. If the roof line of the house will be 15 feet high where the landscaper was standing, how far from the edge of the house will its shadow extend at the same time of day? See the similar triangles below. Well, that's pretty wordy, but basically it all boils down to this. We are going to compare the shadow and the height of the landscaper to the shadow and the height of the house. And these are similar triangles. So if they are similar triangles, we are actually able to set those up as a proportion. All right, so on this one, we're going to compare the heights, right? So we have a height of 6 for the person and 15 for the house. Right, so height to height and then shadow to shadow. And of course the shadow length is also in feet, but that's okay, but we're talking about the height of the person in the house versus their shadow. And so the landscaper's shadow is 8 feet, and that tells us then that our height or shadow length for the house is going to be our x. We then cross multiply, so we're going to take 6 times x. And that's equal to 8 times 15, which is 120. To solve, we divide by 6 on both sides of our equation. And then we find that our shadow is 20 feet. So the length of the shadow. Now we could have used S as our variable. Sometimes when people use S's, they look too much like 5s and they can get mixed up. It's fine to use the S or the X. Doesn't really matter. It's just a variable so that we can find our unknown. And so it works either way. All right, just a minute. So this is the slide that was previously blank, which just seems to happen sometimes on my app that I use. So we're still in applications of proportions, but now we're going to talk about quantities that are inversely proportional. And the easiest way to determine that is to actually try this. So you take your two quantities and you say, okay, as this one increases, what happens to the other one? Well, if it's the opposite, it decreases, then we know that it's going to be an inverse proportion. If it decreases on one and increases on the other, same thing. Here's an example down here. The time required for a trip of a certain length is inversely proportional to the speed of travel. The faster you go, so your speed is increasing. The quicker you get there, so your time is decreasing. So if you can think of the two quantities that are in the problem, and then compare them, that will help you decide. Sometimes it just tells you it's inverse, and that's handy. And this is one of those, okay. The length of a wrench is inversely proportional to the amount of force needed to loosen a bolt. A wrench 6 inches long requires a force of 240 pounds to loosen a rusty bolt. How much force would be required to loosen the same bolt using a 10-inch wrench? Now, a lot of you have experience with this. You've actually used a wrench for trying to loosen a bolt, and you know that if the wrench is longer, I don't have to put as much force. So as the length of the wrench increases, the force decreases. This tells us it's inverse, but it's just good to think about that. How would I know this if it didn't say? Right? So we need less force for a longer wrench. Let's write that out. Just food for thought, because really this class is a lot about thinking through the details of a problem. Okay, so follow these 3 easy steps to set up your equation. What two quantities are you comparing? Place the data according to direct or inverse, and then cross multiply. All right, so let's look at this. If we look at the fact that we have a 6-inch and a 10-inch wrench, we can use those, right? Those are my two quantities. So I have a 6-inch wrench and a 10-inch wrench. So remember what I told you about putting the things that are the same. These are the wrenches. They're both in inches. I have a 6-inch and a 10-inch. And then on the other side, I have to place the other. Now here's what happens when it's inverse. If I have an inverse one, then notice that the 240 goes with the 6 inches. I have to put the 240 diagonal from the 6, not across from it. Now remember, with direct we would put it here. But because it's inverse, I have to turn this one upside down from what I would have done for direct. So that's why the 240 goes on the bottom denominator instead of the numerator. And then here's my x. So I've got 10x equals 6 times 240, and that is 1440. We're going to divide by 10. It's always nice to divide by 10. And then my x is 144 pounds. Now remember, we decided that we'd need less force for the longer wrench. So for the 10-inch wrench, we need 144 pounds of force. Okay, so I hope that that's helpful and that makes sense. All right, here's the next one. A pair of belted pulleys. So belted pulleys are usually an inverse, but we'll talk about this in a minute. A pair of belted pulleys of 20 inches and 16 inches respectively have diameters, I'm missing a word here, of 20 inches and 16 inches respectively. If the larger pulley turns at 2,000 RPMs, how fast will the smaller pulley turn? Hint, in a belted pulley system, the speed of a pulley is inversely proportional to its diameter. And what that means is the larger the pulley, the slower it goes, versus the smaller the pulley, the faster it goes. And so let's write something out about that. The smaller pulley turns faster. And if you've seen this happen, you would understand that as my large pulleys pull, right, they're belted together. So as one turns, the other one turns, and the big one's not going to turn as many revolutions as the smaller one. So the smaller one turns faster. And let's say more RPMs than the larger pulley. Because you really have to think about these. So when you see a similar problem, okay, I'm on belted pulleys again. Well, what's happening there? So the bigger the pulley, the slower it goes. The pulley increases in size on the diameter, and it decreases RPMs. So that's how we know it's an inverse. And my pulleys are 20 inches and 16 inches. And it tells us that the larger pulley, which is the 20-inch one, turns at 2,000 RPM. So we're not going to put it across, right? No, not there. We're going to reverse this one, or flip it upside down, basically. And the 2,000 has to be diagonal from the 20. There's my x. So 16x, right? 16 times x, 20 times 2,000, and then we simply divide to solve. We're going to divide by 16, and x equals 2,500 RPMs. And remember, that was the speed of the smaller pulley, right? How fast will the smaller pulley turn? Well, 2,500 revolutions per minute. All right, that's the smaller pulley. And it turns faster than the larger, which was 2,000 RPMs. All right. A truck driver covers a certain stretch of interstate in 4.5 hours, traveling at the posted speed limit of 55 miles per hour. If the speed limit is raised to 65 miles per hour, how much time will the same trip require? Well, this one is also inverse, because the faster we go, the less time it takes. Now, we want to remember to get this set up correctly, so I'm going to take my 55 to 65, right, miles per hour. I'm going to put those on the same side. This helps me get this right. If you don't do this on the inverse, it's often that you don't get them set up correctly. And you notice that I'm not even showing you the other ways to set these up, because I want you to find a consistent way that works for both direct and inverse. Lots of ways work for direct, not so much for inverse. And then it takes us 4.5 hours going 55 miles per hour. So we're going to put that diagonal, and I'm going to go ahead and just change that to 4.5. And then we can cross multiply to solve. So 65 times x, 55 times 4.5, that's 247.5. We divide by 65 to solve. And x equals 3.8 hours. And so remember this, faster speed equals less time. And you can catch it if you mess this up, right? You set it up, this part, if you did this upside down, then you should realize that when you solve, because the numbers shouldn't make sense. If I'm driving faster, it should take me less than 4.5 hours, because that was my speed, or that was my time for that speed of 55. All right. So I think I'm going to stop this video. I have about 3 more problems for the next video, and we'll finish it on that one.